This video tutorial is intended for Stage 6 software engineering students, particularly in the New South Wales software engineering syllabus, particularly the first unit of work, Programming Fundamentals. Credits in this video can be taken from the following sources. And the syllabus dot point that we're looking at today is specifically the use of number systems, binary, decimal, and hexadecimal, as well as an ability to represent integers using 2's complement. So binary, decimal, and hexadecimal. It's not all that complicated. Binary, decimal, and hexadecimal are three different numbering systems. Now, in normal Roman numbers that we use every day, they're decimal. That's 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All of our numbering system that we use in the Western world is made up of a combination of decimal numbers. Now, the problem with that is that computers don't actually understand decimal numbers. They actually only understand binary numbers. And that binary bit can either be a 0 or it can be a 1. So it is what we call base 2. And as you see here on the table below, binary bits like to hang out in groups of 8. So I've drawn this table here with 8 particular spots. 8 bits together make a byte. And these are the amount of numbers that we can represent. So with this first, this can either be a 0 or 1. So the greatest number we can represent is 1. If I use 2 place values, the 2 and the 1, and I have a 1, 1 there, that value would be 3. 1, 0, the value would be 2. 0, 1, the value would still be 1. And so on and so forth. And because it's base 2, it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. As you start moving through binary numbers, 1, 2, 4, 8, 16, 32, 64, 128 will be ingrained in your memory. Unlike binary, hexadecimal is base 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Obviously as well, if I wanted to represent 0, there's a 0 there. It's called base 16 because there's 16 potential place values. When I'm looking to convert a number, either from binary to hexadecimal or vice versa, I split the number in half. Apologies, I split the number in half. If it's a binary number, I split that in half. If it's represented as a hex number, like 9F, I split those two in half and do the conversion that way. That's the easiest way to do it on pen and paper. Here's the most complicated component of this, and it's 2's complement. 2's complement is a method for representing integers in binary form. Particularly useful when I wish to store negative numbers. Because the premise of this table is that these are all whole numbers. What happens if I wanted to store negative 3, negative 4, negative 8, negative 16? I'm kind of at a loss. I can't have a negative sign on the front. Ergo, I have 2's complement. 2's complement is a method for storing negative numbers whereby which I use half of the potential possibilities, so I don't go for all the way. So 1, 1, 1, 1, 1, 1, 1, 1, all the way along here. If I added those all up, would be 255. So I can't use all those place values, assuming in signed numbers, so in negative and positive numbers and in 2's complement. What I have to then use is all of the values that I would have been apologies, I would have been using store numbers bigger than 128, I now use for the inverse or the flip side of them, their negative equivalent. So to convert a number, I suppose going back here, half the values are used for the positive representation, so positive 0 to positive 128. The other half are used for the negative representation of the number, so from 0 to negative 128. So to find a 2's complement number, particularly when you're trying to find the negative version of that. The 2's complement for 3 would be 3 as you would normally have it here. The 2's complement for 64 would be 64 as you would normally have it. The complicated component comes when you're trying to find negative 64 or negative 6 or negative 4 or negative 2. How do I know what the flip side is? So to find the flip side, you convert to the binary of the number. You invert the binary digits and you add 1. or always remembering that 1 plus 1 in binary is 1, 0. So let's go through a quick example here. So say I had, I think I had it on the slide. I wanted to do the number 13. So here's the number 13. Yep, and as I always draw down here, I'm going to do 1, 2, 4, 8, 16. Oh, I lost my mind a bit there. 1, 2, 4, 8, 16, 32, 64. We're getting smaller. Sorry, guys. 128. 1, 2, 4, 8, 16. This is embarrassing watching me draw this for so long, but that's okay. 32, 64, 128. Now, in 2's complement, 13, 0, because it's a positive number, 0, 0, 1, 1, that's 12, 13. That is 13 in 2's complement. In normal binary unsigned bits and in 2's complement, that's 13. Now, what I'm actually looking and what I'll do here with 13 is I'm not actually going to look for 13, apologies. I'm going to look for negative 13. So that's 13. Yes, happy. What's negative 13? Okay, so in 2's complement, all I'm required to do is invert the bits. So I'm going to do that. 1, so a 0 becomes a 1, 1, 1, 1, 0, 0, 1, 0. Okay, I've inverted the bits and now I add 1. And sorry, I'm going above and beyond my original binary 13 number. I just know this is going to be easy. 0 plus 1 is 1, and then it's 1, and then it's 0, then it's 0. Sorry, I tried to get 1, 1, 1, 1. So that is negative 13 in binary, in 2's complement binary. Now, how could I prove that? How could I go about proving that? And I'm going to see if I can add some text. I'm going to try Magic Write. Oh God, I'm very excited. No, it's going to be too hard. That's embarrassing. Let's just try adding a text box because I cannot be bothered to type this number out. Oh, good, my paragraph text has gone there. This is just a whole video tutorial watching me do things. 1, 1, 1, 1, 0, 0, 1, 1. Perfect. So you don't have to watch me use my mouse to type out this number. So I reckon, I'm fairly confident that this is my number now. Okay, and I'm going to make my life easier by separating it out like this. I'm fairly confident this is my answer for 13. Well, how could I prove it? How could I make sure that 100% I'm confident with this being the answer for 13? Well, let's see how we could reverse the process. Let's put our little draw tool under here. That's 1, it's 2, it's 4, it's 8, it's 16, it's 32, it's 64, it's 128. Okay, so we know that the first step is adding 1. So we know the first step is adding 1. Now, sometimes it's easier to subtract 1 once I've inverted it again, but I am going to subtract 1 from this number because this number is nice and easy to do that from. So let's invert the bits first. So I know I've inverted them, so let's invert them back. 0, 0, 0, 0, 1, 1, 0, 0. Okay. What's my answer? Well, I like that I also didn't provide that. This is not going swimmingly, guys. I apologize. 16, 8, 4. Okay. I'm looking for negative 13 when I invert the number 1 and 1. Yeah? My answer is 12 plus 1 is 13. Now I have to add it again rather than subtracted it again because I've done the inverse first. And that's it, guys. That is how I can prove that my conversion is correct.